Hello, so today we are going to start Chapter 2. Chapter 2 is about conditional probability, which can be understood as an extension of the previous chapter. So, in Chapter 1, we learned a basic framework to understand probability and basic how to understand randomness, like event, experiment, outcomes, and some operations like intersection, union, complements. Uh, so they are just basics. Today, we are going to learn a little more advanced concept, which is called conditional probability, and it will be more practical. And I'm showing you it's very useful. And in many examples, the concept is misused. So I'd like you to pay a little more attention to imagine how we can use this concept in application. So in case you have these textbooks, you can find the concepts in those chapters. Again, so this chapter can be quite different from the existing textbooks. So there may not be like one-to-one mapping between like what I do and what you see from the textbook. But like I encourage you to use the keyword to search for the materials to read. That's, I think, better way to find a reference. So let's think about an example first. We are going to consider a promotion and discrimination example. So suppose that someone is wondering if female police officers are discriminated in their promotion decisions, whether it is true or not. By the way, I'm not saying any political message here. It's purely example. Of course, the numbers are like fake, made up numbers. So, of course, discrimination is bad, but I'm not saying there exists or there does not exist discrimination or not. I don't know. I'm just giving you how to study, how to investigate the data in regard to discrimination. But I'm not saying it cannot be perfect, and the real data is more complicated, and there are a lot more things to consider in this sensitive discussion. So please understand. Just take it as an example. So suppose that you have data about many police officers' discrimination decisions. So this table is a frequency distribution table. So there are the data observations are about promotion candidates, like police officers who maybe applied for promotion or who are considered for promotion. And we classify those candidates into 4 different categories. Like first, male and female, because we would like to compare across gender, and the results promoted, whether the police officer was promoted or not. So we have these frequencies. They are the count, the number of observations for each category, for each outcome. So, for example, there are 288 male promoted police officers, but there are 672 male police officers who were not promoted. Again, the numbers are fake, so and of course we are assuming like a purely imaginary situation. So now we are going to use some notation. I'm going to use M for male and F for female, right, intuitively, and I'm going to write P for the result of being promoted, right? So M, F, P are the notation for the events, the basic events we are going to consider. And remember, we learned the complement of an event is the negation of that event, or the event that the original event does not occur. So like P complement, P superscript C stands for promotion does not happen, which means a candidate was not promoted, right? So we can rewrite the table using our notation in this way. So this is a summary of the data. You can imagine a full data like in Excel, but I'm not like but as you know, it will be a long data with like several hundred observations. So I summarized the data into 2x2 table. That's enough to analyze what we are going to do here. So then, first, simple question. What is the probability of F intersection P? So F stands for female, P stands for promotion, and remember this cap, we call this F cap P. So cap, or like inverted U shape, stands for intersection, which means two events happen at the same time. So remember, just in case if you did not watch the previous video or don't remember what I'm saying, I strongly recommend you to go back and review chapter 1. And then, so you have to calculate probability of like a police officer is female and promoted. Stop the video if you need time and do the work. Okay, I assume you answered this question. So let's see. So this event F and P is only this outcome. So there are 4 different outcomes. Among those 4 different outcomes, this event intersection includes only one outcome because P and F have to be satisfied at the same time. So there is only one outcome, and that means there are only 36 candidates observations that satisfy this event. Then what remains is to calculate the denominator. Then how many? Out of how many observations? We have only 36, right? It's easy. Just add 4 numbers. Excuse me. So the sample size, the total number of observations is 1200. So if you sum these 4 numbers, you have 1200. Out of 1200, we have only 36 observations that satisfy our event defined by the intersection. That's 3%, right? So now I'm going to give you another exercise, the same exercise. Now do it by yourself. If you need to use Excel calculator, that's fine. So just answer it by yourself. Okay, so the answer to this question is 24% because there is only one outcome that satisfies this event, and out of 1200 we have 288 observations satisfying this event. So the probability is 288 over 1200, which is 24%. If you had a calculator, it'll be super easy. So then, okay, now so far we have calculated 2 probabilities. One is the probability of promoted female police officers, which was 3%, right? Female and promoted, right? Promoted female officers. And the other probability we calculated was the probability of promoted male police officers, which is 24%. So then, if you compare these 2 probabilities, you may think that the probability of promoted male officers is like 8 times larger than that of female officers. Then can you say this is an evidence, this proves some kind of discrimination exists there or not? Again, it's fake, so okay, I will answer this question. So the point of this question is I'm asking you if comparison of these 2 numbers is fair for our purpose. So to to say something about discrimination. Can you compare these two numbers? That I think the answer should be no. I think it's no, because what we are comparing is, so think about the event we calculated the probability for. So the first event is defined this way. You randomly choose a candidate or randomly choose a police officer, and you are checking if that candidate is female and promoted at the same time or not. So just like there is a pool of police officers, and choose random police officer and see if this is satisfied or not. Same thing for the other probability. We are looking for male and promoted. Then the problem here is we are checking actually two conditions at the same time: female and promotion, male and promotion. So gender and promotion. Two conditions are checked at the same time. But the problem here is, regardless of promotion, the candidate pool size is quite different for male and female if you ignore the promotion results. So that is, regardless of the promotion results, in our data, there are only 240 female candidates, while there are more than 900 male candidates. So if you just randomly choose a candidate, regardless of the promotion result, you are going to see more male candidates. Because of the first condition, already comparing these two events is not fair, because this part is the only difference, but that part causes a huge difference in their pool size, right? So it is just obvious. Even if there is no discrimination, it is like more natural to came across more male police officers than female police officers. And so just because there are more male police officers, there will be more promoted male police officers, just because there are more male, right? That is possibility. So comparing these two events may have this distorted pool size problem. This comparison cannot rule out this problem, and so we cannot draw a strong conclusion out of this comparison. So this is the motivation why we need to consider another probability concept. So I'm going to talk about that in the next video. See you later.